Okay, well, good morning. I'm Professor Jim Ritzy from the EE department, and let me welcome everybody to the first of our colloquium for this quarter, EE colloquium. So I noticed a mix of students and faculty and visitors from graduate students and undergraduate students. Let me start with just a little bit of housekeeping. So if you're taking the colloquium series for credit, you need to attend and sign in. Attend 5 out of 6 seminars this quarter. So today we're very pleased to have an excellent speaker, Professor Robert Heath. He was here yesterday to give our annual Lytle lecture. Some of you may have been able to attend that. This is a different talk though. And Robert's from the University of Texas. He did his undergraduate work at University of Virginia, along with his master's there. And he has a PhD from Stanford. And he's been at UT Austin, I don't know what, 15, 17 years, something like that. And he's very active in a number of different areas of communications, both from the hardware side and the algorithm and performance analysis side. Just let me mention a couple of his other activities. He's also been a CEO of MIMO Wireless and also a former Chief Innovation Officer of Kuma Signals, which are both in the Austin area. So I know we have a lot of interest in innovation, and Robert's been at the forefront of a lot of that. He's also the recipient of a number of awards, including being an IEEE Fellow, but one of the most recent ones is the Best Paper Award, the 2017 Marconi Award for the transactions on IEEE transactions on wireless communications. So Robert's going to talk today on millimeter wave communication. And right. Please help me welcome Robert.
Thank you. All right, it's great to be here with such a full audience. You know, the idea of giving course credit for this talk, I really like it. It's definitely helping the attendance out. So I'm pleased to talk to you today about a topic that's a great interest for me, which is millimeter wave communication. And I'm going to tell you a little bit about some recent work that we've been doing in what's broadly called out-of-band information for millimeter wave. So I'm going to explain what that is and explain how that makes millimeter wave work better. And this is joint work with Professor Nuria Gonzalez-Peralchik, who has collaborated with me on many of the topics I'm going to present here today. So first off, a little bit of introduction here on millimeter wave communication. So I got interested in millimeter wave really because of the use of multiple antennas. So I started my career as a graduate student looking at this area of MIMO communication with multiple transmit, multiple receive antennas. And that technology is now used in wireless LAN, it's used in cellular, so it's everywhere. And it turns out that this technology also has great potential in millimeter wave systems as well. And the reason is that, first of all, in millimeter wave systems, the antennas, they shrink because the efficiency of the antenna is typically proportional to the wavelength. And so millimeter wave antennas are small, which is good because you can squeeze them onto your phone, but it's bad because you don't capture a lot of the energy. And so the use of antenna arrays allows you to capture a lot of the received signal, as you can see up here, and also allows you to focus the transmitted signal towards the receiver. And this leads to higher received signal power, and it reduces the effects of interference, among other things. And so in millimeter wave, the use of multiple antennas, at least for most commercial applications, is really critical, especially the consumer ones. And then, so this is not just, we're not talking about just a few antennas like you might see in your phone now, but maybe even dozens of antennas or more. So this is an example of a handset. This is a Galaxy S7 mock-up. And then if you can look there, it's a little bit hard to see with the contrast, but there's these, you see these gold little circles here. These look like antennas. In fact, these are not antennas. These are little ports to plug into the antenna. And then there's, if you zoom in on that, you can see there's actually the antennas themselves are just a fraction of a millimeter. So they're actually really just covering the edge of that phone there. So the antennas can be small. So what's really cool is that we can have both large antenna arrays and in a small form factor. So That's very exciting, and this makes millimeter wave communication new and different, and introduces a lot of challenges both on the signal processing, which I'm going to tell you about, as well as the hardware implementation, RFICs, and mixed signal. Now, one of the benefits, so I'm going to summarize like 3 of the benefits of the large antenna arrays here. So the first thing is that if you use the antenna arrays in the right way, and there's different configurations of this, but this is an example of what's called a hybrid architecture where you do some of the beamforming using analog components and some of them using digital components. You can get the benefits of MIMO communication in the sense of sending multiple data streams. And so you can get the benefits that we enjoy right now in cellular and wireless LAN, also at millimeter wave, if you use the antennas correctly. Another intriguing benefit is from a system level perspective. And so if you were to build a cellular network using millimeter wave, the amount of interference you would get from other base stations would be roughly the same as at lower frequencies without the directional antennas. But with the directional antennas, you actually reduce the interference caused to other users, and so the performance that every user experiences actually is better. And this is something that's a little bit surprising, and so millimeter wave can actually work even better than lower frequency systems, and it gives you a multiplier in the system level rate. So, you know, the average rate in a cell, instead of being 100 megabits per second, is 200 megabits per second. And then the third thing, which is also kind of intriguing, is that the use of these antennas, it opens the door for a very interesting kind of spectrum sharing where 2 carriers share the entire millimeter wave spectrum that they have acquired a license to without any coordination at all between them. They could have, you know, one base station there, one here. They could even be on the same tower. They can, and they can serve all the users independently without respect to the other system, and they can take advantage of the wider bandwidth there. And so what it means is that instead of taking the spectrum, splitting it in half and giving half to each carrier, if the carriers combine their spectrum and share it, we get the benefits, not quite of double the spectrum, but about, let's say, 50% more. And that isn't possible at lower frequencies because at lower frequency systems, you can't form and shape very narrow beams. You can't get this level of interference reduction. So that's just it's a cool feature of millimeter wave that really just goes beyond the basics of using lots of antennas and getting a high SNR. Now, one of the biggest challenges in millimeter wave systems, bringing them to commercial applications, is configuring those antenna arrays. And what I mean by configuring is really figuring out how to point the beam. Or there's more complicated techniques which involve more complicated looking beam patterns, but you still have to figure out how to launch the energy into the propagation environment, and the receiver has to figure out how to couple that energy and apply the receive signal processing algorithms. So the state-of-the-art approach, which is used in commercial systems, is what's called beam training. And I explained a little bit about this in my talk yesterday, and I'll talk about it briefly today as well. But the basic idea is that you send information in different directions and then wait to see which one of those went through. And so the receiver might also listen in different directions, and you can see that if I have four transmitting directions and 4 receiving directions, there's 16 possible pairs. And so the more beams you have, which occurs when the beams get narrower with larger gain, the more the pairs you have to cover. And that's a big source of overhead, but that's the state of the art. That's what's used in all the commercial millimeter wave products available now. Admittedly, that most of us probably don't have. I have some in my lab, but I don't have any in my devices. Now, from a research perspective, we've been looking at other approaches to solve that problem. And one of the more recent ones we've developed is a method that's called compressive channel estimation. And here, the key idea is that instead of pointing the beam in different directions, we launch the energy into the propagation environment using random-looking beam pairs. So instead of sending it in an omni fashion, so maybe I send a little bit here, a little bit over here, a little bit here, and then through the process of taking all these observations together, I can actually measure the whole propagation channel. And so that's compressive channel estimation. It's not used in any commercial systems, but it does allow you to estimate the entire channel, which is not possible with the beam training. And the problem with both of these approaches is that there's still quite a bit of overhead associated with pointing the beams or just doing this compressive measurement process. And what I'm going to tell you about now is an approach to reduce this overhead here through the use of what I call out-of-band information. So let's first of all look at what is the state of the art. Well, I mean, most of the research, the papers that you see that do not deal explicitly with beam training or channel estimation, they assume that there's access to this right here is, of course, a genie. And those of you who have taken information theory, you kind of get this joke here because there's in information theory, the genie is normally assumed to give you everything about the system, the environment, the distribution of the noise, the distribution of the transmitted signal. It gives you everything but the information you're trying to decode at the receiver. And of course, if you had a genie, you would ask him what the information was. You wouldn't ask about, give me the statistics of the environment. So most of the work, of course, assumes this genie, which, I mean, is not realizable. It may be good for writing papers, getting a dissertation, getting a nice job, buying house on the lake, or one of these houseboat things. Well, maybe you need a couple jobs for that. But unfortunately, not really useful in practice here. So what I'm going to describe here is an approach where we use other information that can be derived in the wireless communication link. And some of it is, and it's all different kinds of site information. So one of them is position. So if I happen to know where the transmitter and receiver are, can I exploit that? Another is out-of-band information. So if I have a communication link at a lower frequency, can I infer anything about that to help my millimeter wave link? And then finally, the sensors. So I have sensors in the device, for example, gyroscopic sensor, it tells me the orientation. Can I exploit that information to help improve communication? And the interesting aspect of this is that, so when you do the beam training, you are using the communication resource to figure out where to point the beam. But while you're doing that, you're not communicating, right? It's like establishing the link. So there's a lot of wastage there. The approaches I'm going to tell you about use other resources that in some sense are free. And so you're not taxing your communication resource. You're using some other kinds of site information. And so that's very attractive because then the overhead that you need from your communication resource goes down quite a bit. So we're getting a little bit of that aspect of the genie, but we're doing something that's realizable here. So I'm going to start off by explaining each of these concepts. I'm starting with position because I think position is the one that we can most easily relate to intuitively. And then I'm going to move on to multiband. So the basic idea of position information is motivated by the application of millimeter wave into vehicular systems. And I'm a big proponent of this because vehicles, as they're becoming more and more automated, have a lot of sensors. And so the typical automated vehicle, we had Ford on campus last week and showing us their car. I mean, they had 2 LiDARs, either 6 or 8 cameras, a forward-facing radar, a rear-facing radar, as well as ultrasound sensors. So they're generating a lot of data. And when you have a lot of cars that are all automated, they can share that data to coordinate their actions and to drive more efficiently. So if cars can communicate, they can platoon together. And what that means is they follow each other closely, reducing the normal safety gap that we have. And then they occupy less space on the road, so we can fit more cars on the road, and they can go faster together. So it's really good for everybody. And believe me, that is much more efficient than spending like 10 years to add another 2 lanes on the road or to build another bridge here. So it's very efficient for the perspective of taxpayers, also makes driving safer, more efficient. And then finally, when you're at the point of being able to drive or ride in the car while the car is driving for you, then you can use that time for better purposes, like YouTube cat videos or catching up on homework, sleeping, reviewing my talk here again and again in the future. So there's a lot of things you can do there. Now, one of the things that's happening in automated driving, that there is a communication protocol that's already been developed. It's called Dedicated Short Range Communication, or DSRC. It's been developed over a period of 20 years. And what it is it's like it's built around wireless LAN, and one of the features of it is that the cars broadcast a heartbeat. So 10 times a second, they broadcast, here's where I am, here's my position and velocity, and there's some other information that goes in there as well. It's called the basic safety message. And then, so I'm coming around the corner, I could be listening, oh, there's a car coming, I can't see it, but my car could know there's a car coming around the corner, and then a forward collision warning application might say, hey, apply the brakes, or it might give me a signal to do something. And it could actually take control of the car as well, depending on how it was implemented. But the main message here is that there is spectrum already there, 5.9 gigahertz band, and there's hardware, and there's a communication protocol for cars to exchange position information. And there also is hardware that goes on the base station, they call it a roadside unit, to pick up that position information. They use that to monitor traffic. And this hardware is already commercially available. It's pretty cheap. I have some of it in my lab. It is not widely deployed yet in vehicles for strange political reasons, though it's now in Cadillacs right now. And in Japan, they're starting to deploy it in Toyota cars. But basically, there's going to be there's a wireless protocol broadcasting position. So if we know the position and we have a line of sight communication setting where, and line of sight means that the transmitter and receiver can see each other. An optical line of sight is very similar to what line of sight would be in millimeter wave. And if you can see here, so if I'm doing like beam training from this car, let's say, if I don't have any sight information, I need to try all of these different beams and see which is the best. But if I have sight information, then I can say, well, okay, I'm located here. This roadside unit is located here. So one of these three beams is probably going to be the best one. So I just try those few. I don't try all of them. And so that reduces the amount of overhead dramatically, especially when you consider that both the transmitter and the receiver need to try pairs of beams. And this works also for car to car, as well as to the infrastructure here. So some of the, what is the improvement that we can get? Well, so we developed a mathematical model that includes the uncertainty. Because position information, by the way, is not perfect. GPS, you are typically getting about a 2-meter accuracy. That's in fact not even good enough to know which lane you're in. By the way, if you're in an urban corridor, GPS may not even work, which is a whole nother challenge. But so we developed a mathematical model that models the uncertainty in position and incorporates that to figure out how many beams to try. And so we try a few beams based on that level of uncertainty. And then depending on how narrow the beams are and the amount of uncertainty, we can get about a 6-fold improvement in terms of the reduction in overhead. So basically, we can set up that link 6 times faster, and you get more time to use data. Now, that's a rather simplistic approach because the work was really assuming line of sight communication, so the transmitter can see all the cars, which is a great setting. But sometimes, maybe the transmitter's not located very high. Maybe it's like 6 or 8 feet off the ground. Maybe there's a truck parked that's unloading some soft drinks for the store, blocking the signal. So the line of sight approach isn't general enough. So another technique that we've developed is what we call inverse fingerprinting. And so the idea is that there is a technique in wireless position location which is called multipath fingerprinting. This was really popular in the 90s. I suppose many of you were probably not in the UWEE program back then. I hope your graduation rates are a bit better than that, a little bit faster. But anyways, this was before phones had GPS chips in them. And so the question was, how could we locate people from their cell phones, without, of course, knowing where they are? And so one approach is that what they found was the multipath environment, the signature, which is the kind of the angles and delays of the multipaths, is very strongly a function of position. So here, there's reflections on the ceilings, the walls, and the various stuff. Those reflections are a little bit different if I just change my position slightly. And I just change my position slightly, they're yet again different. And so if I went through this floor here, let's say the floor of the auditorium, and I made some measurements of the position and the multipath channel, and then I made position, multipath channel, and I built up a database, then presumably I could come in and make a measurement of the propagation channel and query that database and get out the position. And so that was what was called multipath fingerprinting. So big topic in the 90s, and there's still papers on that these days. It's actually useful still for indoor positioning where a GPS doesn't work, useful in Wi-Fi. Now, what we do is actually the reverse here. So for us, what multipaths are opportunities for our signal to get from the transmitter to the receiver. So here, there's a reflection off of this truck. That's a multipath. This is a direct path. Here's a reflection off of the building. So there's three, good paths between the base station and this particular car here. And so what we do is, using this position information, we also build up a database where we measure not the multipath channel, but we measure which beams work well as a function of position. And you can see that sometimes when you make the measurement, there's a truck over here, and it blocks this beam, but this one becomes good. So we have a whole lot of measurements of which beams work, and some of them work a lot of the time, some of them never work some of the time. And then based on that information, based on position, we can query the database and figure out which beams might be good. And so in the same story as before, the car can now try a few beams, the base station can try a few beams, and we reduce the amount of overhead dramatically. And we call this inverse fingerprinting because we're doing the fingerprinting in the reverse direction. And so this is a very nice application here of what's called like a data-driven approach. And so in fact, we're not trying to create a mathematical model of the environment. We're really just collecting data and then querying this database and finding out the answer. This is a basic kind of machine learning, in fact. And so this is just an illustration of really what's going on here. So I have a performance plot. So what we do to evaluate the performance here, because we don't have really good millimeter wave equipment we could take outdoors yet, we build a electromagnetic model of a roadway with buildings and with cars. And then we put the cars in different positions according to traditional distributions that are used in traffic studies. So there's like an Erlang distribution that decides the gap between vehicles. There's rush hour, there's non-rush hour. And then we make a whole bunch of measurements of which beams are good from a signal power perspective, and then that's our data that we use in the database here. And then what we see is that so the question for us is, how many pairs do we try? Because we're not trying to get the best beam pair as a function of position, because sometimes the pair is blocked. So what we want is a few good pairs. And the key here is a few. And because I'm going to try a few, I probably don't want all of them pointing in one direction, because if this beam's blocked, that one is also probably blocked too. So I actually want beams that are in different directions such that the probability that all of them is blocked is very, very low. And you can make that probability low by having lots of beams or by picking them very, very intelligently, which is what we do here. And so we find that with even 10 beam pairs, the performance is quite good, and up to 50 is essentially perfect here. And in some calculations, which I'm not going to go through here, but we compared with the state-of-the-art approach for beam training and 802.11ad, and we're about 2 orders of magnitude more efficient there. So about 100 times faster you can beam train. And 11ad, unfortunately, is not very well designed, it's very slow. So it's hundreds of milliseconds potentially to train and refine beams, and we can do that in just a millisecond. So to summarize here on position information, so the basic idea is to incorporate position and to help us set up the communication link. And so there's different things that can do here. So what we have done so far is the data is created in this electromagnetic simulator. We haven't really exploited other features that might be used in a machine learning type algorithm. So for example, the time of day. So there may be a time, like in Austin, the delivery trucks come before 5 a.m. and then they offload their stuff, and then they leave when rush hour starts. And so the conditions that happen before 5 a.m. are going to be quite different than those at like 6 a.m. So that's an additional feature that can be used to train the database. So now not only do I know past positions, but I also know the time of day when the measurements were made. So that's something that's interesting. We haven't incorporated that yet. We're also looking at things like how can we exploit knowledge of the other cars too? Right now we don't do that. But if I know where all of the cars are, then I can, to some extent, I can back solve to figure out which propagation paths are caused by reflections off of cars, and then I know that those are less stable than the other ones. So that's another opportunity there. So we're looking at that now. And then everything I told you about is really focused on this simple idea of beam pointing, where I have like a focused beam and I'm scanning it around. But the more sophisticated millimeter wave strategies use more elaborate kinds of beams, and those need different approaches than what I've described, and that's also what we're developing there. And I think what's really exciting here is we're seeing a really nice connection to machine learning. And so I have 3 students now that are looking at different aspects of machine learning. One of them is looking at deep learning. The other one's looking at like support vector machines and classification. And this is nice because machine learning, what it does is it's bringing in this whole data-driven perspective, which we haven't had in communications. Before communications was, okay, we drive these models, we derive some theory, then we build a complicated system and test it in some other models, and that's kind of the extent of it. And now we're talking about systems which are going to learn from their environment and going to react to it. And I think it's very exciting, and it's a good opportunity for working in this area, and also to get machine learning on your transcript so that you can get a job that pays twice as much as if you don't have it on your transcript. Now I'm going to talk about another source of site information. This is called multiband, or communication at lower frequencies. So the setup here is that now millimeter wave, the way I've been describing it so far, it is being used in isolation. So we have a millimeter wave communication link. We transmit with millimeter wave. We receive with millimeter wave. It's done. But we know that a lot of wireless systems, so cellular, for example, there are communication opportunities at different bands. So almost every provider, they have, maybe they have some spectrum at 800 megahertz. Maybe they have some at 1.9 gig. Maybe they have some at higher frequencies. And depending on where you are located, your phone will shift frequencies. And so some carriers, if they deploy millimeter wave in a cellular context, will operate the device in parallel with the lower frequency. So you might have a phone that it connects at a low frequency, then it tries millimeter wave. Okay, millimeter wave works, let's go there. Oh, millimeter wave has stopped working, let's go back to the low frequency. So the question that, assuming that this is the case, and then the question that we were trying to answer here is, can we use information derived from the lower frequency to help establish the millimeter wave communication link? Now, of course, I can use the low frequency to talk to the transmitter and say, hey, I'm here, let's talk at millimeter wave. That is doable, but that's not what we're trying to look at here. So we're really trying to exploit the band, what I'm calling here band diversity, and in particular, the information about the propagation channel at that lower band, which is something that it's kind of a disruptive idea. Now, when coming up with this problem, so this is typical part of research, right? So you come up with an idea, try to sketch it out, see how it works, and you think, oh, you congratulate yourself, this is a brilliant idea. Then, well, of course, what you should do, if you're an academic, is you go back in the literature and you use Google and IEEE Explore and you try to see if other people have done it. By the way, if you're at a company, most likely at this point, you would not do that, and you would try to file a patent on this. And there's something about the patent law where it's like if you don't actually look for the prior work, that's actually okay in some sense. It's like, oh, gee, I didn't know there was that prior work there. And then the patent attorney will write the patent in such a way that millimeter wave will call, it'll just get a new name. So it won't be called millimeter wave, it'll be called communication means. All the stuff will be abstracted, and so then 10 years later when the patent issues and someone's fighting over it in court, they can say, oh yeah, but here, we meant terahertz, not millimeter wave. I mean, it's, anyways, so companies, you don't necessarily look up the prior work, and I don't mean this as any kind of an insult towards people working in companies. I'm just pointing out that there's sort of a difference in the way that people do things, and difference in the what's important as well when you're at a company. Publishing is not often a high priority, but filing a patent might be. So we went back to the literature, and we found an interesting set of different approaches where people had been applying this idea of using one band to communicate another band. And one of the first papers we found was in 1998, and I'm sure there's papers before that, but this is one of the earlier ones. And in cellular systems, most of the spectrum is frequency division duplex. And so what that means is that the phone talks to the base station on one frequency and listens to the base station on another frequency. And those frequencies are separated by roughly 10%, maybe a little bit less, so depending on which band you've got. So maybe you talk at 1.8 gigahertz and you listen at 1.9, something like that. And so this initial work, they were trying to figure out, okay, if I do some beamforming based on the channel that I'm listening to the mobile on, to talk to the mobile, how much correlation is there? And so there was a lot of work on this. It's called FDD reciprocity. And so in a sense, what we want to do is a similar idea, except that we want to learn from the channel at, let's say, 2.4 gigahertz and do it at 60 gigahertz, do something. And the gap in the carriers is vastly different. And that makes it challenging here. And so there's been a couple other papers as well. There's been some nice experimental work from Rice where they've been trying to develop some better beam training approaches using the low frequency Wi-Fi signal. So there's been a few papers. And then finally, there's been some experimental work on propagation channel. And I'll highlight this up here, which comes from this tech report here. And this is a channel measurement. This is angle, azimuth and elevation angle. So what they're plotting here are the strengths of dominant multipaths, looking in a two-dimensional direction here. And this is at 5.8 gigahertz, 14, and 58.7. And what you see is that, this is a line of sight channel, so this is probably the best case. But what you see is that the line of sight path at the low frequency is the same at the higher frequency. And then there's more multipaths here at the lower frequency, but there's a lot of congruence here. I mean, it's not exactly the same, but it's also not totally different either. You know, there's a lot of blank space here, that blank space is here, and it shows up here as well. So this gives us some hope that there's enough congruence in the information in the channel to at least offload some of the overhead in establishing the millimeter wave communication link using this idea. Now, let me explain to you why the channel is not exactly the same. I mean, the fundamentals of Maxwell's equations, all that stuff works at 2.4 gigahertz, it works at 60. I mean, that stuff doesn't change. That's all good theory there. What does change, though, is the effect of the objects in the propagation environment. And so one of the things that's really important in cellular systems is diffraction. So diffraction is this bending of the radio waves around sharp corners. And that's what leads to coverage in urban areas. So signals diffract over buildings and around the corners of buildings. And any good ray tracing coverage predictor will have a diffraction in it for doing cellular coverage. Millimeter wave signals don't bend as much around corners because the frequency is much higher. So diffraction isn't very significant. But perhaps the biggest one is that, well, there's a couple here. Things that might be smooth at a lower frequency are rough at millimeter wave. So, over here, I don't know if this is going to get this on the camera, but you can see there's like this kind of grid work here. At a low frequency where the wavelength is, many centimeters, this will look pretty smooth. And at millimeter wave, this has got a tremendous number of tiny little holes where the signal can go into and be absorbed there. So reflections tend to have much more scattering, and they're not as specular. So that leads to the energy being dispersed over a bigger area. And then finally, what's called the Fresnel zone, where you can consider a line of sight signal to be blocked, is much smaller at millimeter wave. So if I have a transmitter receiver Wi-Fi and I walk around, I actually don't block that direct signal because the wavelength is big enough that I'm not, fortunately, as big to create a huge blockage. But at millimeter wave, Fresnel zone is very small, and so I can block that entire signal. And so blockage becomes much more important at millimeter wave, diffraction is less, and scattering is higher. And this means that millimeter wave operates also in a different way. And the channels aren't going to be exactly the same because of these differences here. So I'm going to explain a little bit of just the technical challenges associated with exploiting this kind of an information here. And so I'm going to tell you about smarter beam search, weighted compressed sensing, and correlation translation. So the idea here I start off with translation here. And I've thrown in a few equations here, but let me explain the basic idea. Most of the classical work on array processing uses an estimate of the spatial correlation matrix. And so this is the standard things that you're studying in probability. You have a vector, and you want to estimate its correlation. So you take a bunch of outer products, average them up, and you get a matrix. That's your correlation estimate. And then from that matrix, using classical array processing theory, you can derive the angles of arrival of different dominant paths and their power and potentially even their delay. And so you can derive essentially the multipath structure from that covariance information. You can also derive things like the number of scattering clusters, the angle spread. So what we wanted to do, though, is we wanted to translate that matrix that we might derive at a lower frequency to an equivalent one at a higher frequency so that we can apply the same techniques at the higher frequency and then derive, okay, what are the dominant propagation paths? So that's like the idea there. And then let me just illustrate here the challenge. First of all, there are two big differences in terms of resolution. The first is spatial. At the lower frequency, we're not going to use as many antennas as at the high frequency. So the MIMO systems at let's say, Wi-Fi, if you're lucky, you've got 4 antennas on your access point. You might have 3, you might have 2. Probably have 2 on your handset. So you have 4 antennas, but the millimeter wave, as I argued before, might have 32, might have 64, or 512. So there's a change in the dimensionality, and then the relative spacing between the antenna elements also is different. So in terms of wavelengths, they might be both half a wavelength, but the wavelengths are so much smaller at millimeter wave. So what you get is this an intriguing problem where not only do we have to estimate these parameters, but I mean, we also have to, in a sense, extrapolate this spatial correlation because we're operating over many more wavelengths there. So that's one of the challenges here. And then the other challenge, by the way, which I'm not emphasizing here, is also the bandwidth, because the bandwidth at lower frequencies typically is like 20 megahertz maybe, and at millimeter wave we could have 2 gigahertz. So our ability to resolve multipaths is also vastly different. Now, keep in mind, again, we are not trying to estimate the millimeter wave channel. All we're trying to do is get a rough idea of how to start maybe the beam pointing process. So we don't need to have a perfect translation. We just have to figure out what information is important. So we looked at a couple different approaches to do this here. Wow, I don't know what that was. I think that was you. Oh, okay, all right, good. Okay, I got scared there. So this is the correlation translation. And basically, because of this mismatch, even in theory, it's really a tricky problem. But what we did here was essentially that there are well-known forms for the spatial correlation as a function of the angle spread and the scattering clusters. And so if we take the lower frequency spatial correlation matrix, we extract the dominant multipath directions and angle spreads, we can take that information and build the larger correlation. So that was actually the approach we ended up taking. The prior work, they were trying to literally mathematically transform this smaller matrix to another matrix. But it's very difficult for us because we have to go from smaller matrix to much bigger matrix. So we tried that. We have some approaches there, but those weren't as good as the ones where we run the algorithms on the low frequency, translate to the high frequency. So one of the things that we used, how we used this information was in what's called beam selection aided by the sub 6 gigahertz information. So basically, we used a smart algorithm for doing some kind of beam training, and we initialized this based on what we derived from the lower frequency spatial correlation matrix. And this is an example here of what we would do at low frequency and how we'd use that information at higher frequency here. So what you might do in millimeter wave link is when you don't know the directions at all where you should send, you start by sending information on relatively wide beams, because you don't have to do too many of them. And then once you agree on a wide beam, then you refine. So by using the side information we derived from the spatial correlation, we can get rid of that first stage of the wide beam, and we can instead focus on the refinement. And we can refine over a smaller subset there. And then using that, we can reduce essentially one stage in the algorithm, and that reduces overhead tremendously here. Another thing that we did was, so in the algorithms that we've developed for channel estimation that use this idea of compressed sensing, we can take the side information here and we can incorporate it into the algorithm to bias it so that it looks more carefully in directions that we, based on our prior, believe are more promising. And one of the ways to do this was using a weighted compressed sensing approach. And this is like really just gratuitous math to make the presentation look super technical. But the idea is if you've ever seen compressed sensing, there's normally an equation that looks like this. This is a fat matrix. G is a sparse vector. That's noise. And this is an observation. And then the game in compressed sensing is to recover the G, which is, again, sparse, from the observations of y, given that this phi here is fat. In normal linear algebra, that phi would be square or tall, and you'd use least squares. And here you can't use least squares, but the fact that it's sparse helps you. So what we do is we solve this problem in such a way that we find a sparse vector that is more likely to be sparse in the places where we have prior information about there being energy. And it's not always correct, but so you can't over-rely on that information. But if you balance the weighting appropriately, we have found that we can improve the estimation error quite a bit. Now, another thing that you can do, and this is something that we've been playing with a bit, but if you have a good idea where the channel is possibly got good multipaths, if you're making random measurements, like these splotches here are different beam patterns. So this is like a random beam pattern. This is a blue beam pattern. These are PowerPoint beam patterns. These aren't real beam patterns. Those are harder to do. And this is like the directional beam pattern. So if you're going to make a bunch of random measurements, if you have a good idea that over here there's not any multipaths, why make measurements over there? So what we do is we use the site information to customize how we make the random measurements so that we make it only in the directions that are really interesting. And that leads to another reduction in overhead. Honestly, this one is not as big of an improvement as the other approach. But essentially, you can combine them together. So one of them is like in the reconstruction algorithm, you use the site information. And the other is you use the site information to reduce measurement overhead. And so both of those together improve the system performance. And this is just to give you an idea of the kind of rates that you can achieve as a function of the number of measurements. And so we can get about a 2x improvement in rate. And the reason the rate is important here is we're assuming there's a block coherence time. So part of the time you're training the beam, part of the time you're using the channel. So the longer you train the beam, the less time you have for data, and thus the lower rate. And so we can get, with not too many measurements, much better performance than at the lower frequency system. And at some point, depending on which approach that we take, we can actually do worse than the N-band approach, because our site information is not perfect. So at some point, if you over-rely on the site information, then you can eventually do worse than if you didn't have it at all. But that's only when you have tons of observations. So this, I think, it's a really cool area. It's been challenging to work here because it's hard to get all those channel measurements. So we've been collaborating with different people, trying to get access to their channel measurements. And the tricky thing is that when most people measure the channel, so the typical approach is that there's a whole bunch of equipment, there's a bunch of grad students, a bunch of undergrad students, and they're pushing all the equipment around, making all these measurements. And then they come back the next day, and maybe they'll make a whole bunch of measurements at another frequency. But of course, the channels are potentially totally different. Some of the seats are down, some of the seats are up. So for us to really go further and develop models, we need simultaneous measurements, where literally at the same time, in as close to the same position as possible, I am measuring the channel at different frequencies, at millimeter wave and low frequency. And so that'll allow us to build better channel models. And if you have a channel model, you can use that stochastic information to help build better algorithms, because you'll have a good understanding of how often the paths are congruent. And so that's been a challenge. We are trying to work on that, but I have to say our channel measurement equipment just doesn't have the fidelity right now. And there's also opportunities really to figure out how to exploit this information. The ways I described are two of the really simplest approaches for millimeter wave. But if we want to do more complicated millimeter wave with something like the hybrid approach, with multi-stream MIMO, we need more information from the channel than just the dominant directions. So I think this is a really promising area. It makes sense because of the way that millimeter wave may be deployed, but it needs still a tremendous amount of research. So I'm going to wrap up with the final approach here on sensors. And I want to tell you, first of all, about where are the sensors here. Well, in your phone, you've got like inertial sensor. You've got, GPS is a sensor because it's telling you position and orientation. Automotive systems have the GPS, the radar. If it's automated car, maybe it's got LiDAR, maybe it's got cameras. So it's got a lot of sensing capability. If we're going to have a system that supports automated vehicles, I actually believe that we're going to start seeing sensing also at the base station. So for example, if I'm managing automated cars through an intersection, having a radar on the base station that has a top-level view to see all the cars, that's very powerful, because the cars otherwise are stuck with seeing what's in front of them. So having sensing on the base station as well, I think, is also going to be very powerful. And if you think about it, it's an old idea. If you get into flying, so I got my pilot license last year, and it was intrigued to learn, why is the air traffic control tower tall? Sort of like, I guess like when you don't fly, you sort of think, well, okay, the air traffic controllers, they need to be closer to the planes, so they're in the air, right? But actually, they're up high, so they can see the planes on the ground. Because on the ground, you cannot see very well in the plane. You don't have a rear view mirror, and you don't have side view mirrors. And so you're always like, and the wings are blocking you. And so the air traffic control tower is high because it has a bird's eye view of the planes on the ground to manage their flow. So that's the primary reason that they're up high. And so it makes sense for me that we should also push a lot of sensing onto the base station as possible. Now, if we're going to do that, can we get some additional benefit from a communication perspective? So one of the first things that we did, this is actually a couple years ago now, was to look at this idea of, okay, if I have a radar on the base station and I'm using it to track the vehicles, can I also use that radar to reduce the overhead of establishing the millimeter wave communication link? The easiest approach would be I take the position derived from the radar. But I already told you how to do that. So we could use the first part of the presentation, and we just replaced GPS with radar. Same story there. What we've done here is we are working on understanding, in a sense, the spatial covariance matrix of the reflected signal. This is what you get through radar, and correlating that with the communication channel. And so the key point here is that the communication channel is the propagation channel between the transmitter, let's say, and the receiver here. And radar is the channel of the reflected signal. So these two these are not the same at all, but they have some relationship there. So if there's, this is our stately old man here blocking the signal, then there's going to be some radar reflection there, and the communication link is also not going to work as well. So there's some correlation between the information that's measured in both of these, but they're not exactly the same. And so we're working on this right now to understand how, what relationships are there between these two signals and how to exploit that. The other application I've got here is we're doing the same thing with video. And so we've got video cameras, and we're using position derived from video to feed a millimeter wave network. And so we've been looking at tower-mounted video and studying how well you can track traffic with video. This is a problem, of course, people have looked at a lot. And then also putting the video on a drone as well. And then, to test these ideas, we go back into this electromagnetic ray tracer, because the electromagnetic ray tracer, it gives us something that is a more complicated environment than we'd otherwise model, and it takes the place of doing the real experiments, which we don't have. And so there we found that we could get a lot of congruence between the information of the radar and the communication channel, surprisingly here. So this is I think is a new and is maybe on the crazier idea side. We're working with Nokia right now. They're very excited about this, and we're trying to test our algorithms on their 5G millimeter wave prototype. So we're hoping to do that probably in 2018 timeframe, but right now we're developing a lot of the theory to understand things like the range. So when are you radar coverage limited? When are you communication coverage limited? And then we'll be able to do some experiments where we can test at least the ideas of tracking vehicles and doing the communication more efficiently here. And I think there's a lot of work to be done. I just talked about radar, but using video is also interesting. Using the gyroscopic information. Orientation is a big deal. When you change the orientation of the handset, you change where the arrays are located. And instead of having to retrain, you just know, okay, this path was good. Now I'm like this, so this path is still good. So all those things are important. And I think, again, here machine learning is really critical because it provides a mathematical tool that you can use to uncover correlations even when we don't have a good prior model. So we can't build ourselves on the whiteboard a good model, but machine learning can to help us figure that out. And maybe then we can learn to build a better model. So just the last here, I'll tell you a little bit about what we're doing at UT. So one of my big interests is the application of millimeter wave to vehicular systems. And so I started it's not quite a center, it's called an initiative, SAVE Sensor Aware Vehicular Engineering Systems, in collaboration with 2 centers and several faculty here. And so we've got now a whole number of companies, Toyota, NXP, Fujitsu, Honda, AT&T, Huawei, TxDOT. Actually, Qualcomm just joined as well. And so we had about $1 million of funding from all of these companies. They're funding about 10 students on all different applications of, many of them are millimeter wave, and some of them are related to automated driving, some are related to more efficient positioning. So it's funding me and several of my colleagues as well. So these are some of the topics that we're investigating right now in the context of this new center here. And the other thing is, even though everything I've showed you here is really, it's all generated in simulation, we are doing our best to have develop experimental platforms. And so we've got hardware from National Instruments where we can do millimeter wave up to several gigabit per second links, so 2 gigahertz channels. The hardware is not as flexible as we would like to do like high-speed outdoor tests, so we're still working on alternatives there. But we've got a couple different millimeter wave platforms. We've got software-defined radar. We've got some off-the-shelf radars. We've got some LiDARs. We got the video cameras. So another aspect of the project is doing sensor fusion for automated driving. And then once we get that worked out, then we're going to do sensor fusion for millimeter wave communication as well. And that's interesting. And then, just to give you a sense of some of the ways we're trying to test out the out-of-band ideas. I mean, we're looking at the positioning, the DSRC, the radar, the camera. So we're making measurements now so we can develop good models for error and in line of sight and non-line of sight and use that to initialize our simulations. So with that, I will wrap up here. So basic summary here is that millimeter waves has great promise for high data rates, but we need to configure the millimeter wave link efficiently. If we don't configure it efficiently, we're going to spend most of the time trying to configure the link and hardly any time using the link. And that's not very efficient use of resources. There's a lot of sources of site information that can help us. So I gave you 3 examples. I mean, position information from another communication band, as well as information from sensors. And all these sources of information have different pros and cons, interesting trade-offs associated with their exploitation. The whole idea itself is really new. I mean, cellular companies have not thought about really exploiting this information in the cellular system. I mean, a base station right now, there's no port where you plug your radar in. I mean, it just doesn't exist. There's not a protocol for taking the radar and putting it into the base station. It's not there. But we are working with the companies, trying to convince them that having this kind of information flow can be very valuable. And so I'm hoping that we're going to be able to establish the viability of this, and then this is going to change how maybe not 5G, maybe it's 5.5G or 5.9G or 6G works in the future here. And I think there's a lot of research challenges here at signal processing, communications. I didn't really touch on the electromagnetics devices, but of course there's many problems there that need to be solved. But I think this is a good opportunity to develop new models, to do new analysis, and also use new tools on these problems. So that's it. I'll take questions.
So we have time for a couple questions. Yeah.
So the main motivation you cited for pursuing the site information is that they can be obtained relatively free, but in information theory there's no really free lunch. Because like you said, you need more like real-time data in order to actually have them be useful in many applications. And wouldn't that also mean that you have to kind of use them more? Like maybe broadcast more or listen more on a different frequency band, for example. And that kind of uses up that spectrum and kind of reduces the spectral efficiency in that domain. So to what extent can you push like this direction? Yeah, so at some point you're going to end up sacrificing some other band or something.
Yes, this is a good question. So I'm supposed to repeat the question for the audience, for the web audience. I think the question was, isn't there the no free lunch principle here that we can't use the information in the other bands without some cost? And I mean, this is true, but the thing is that the perspective is really that we're not redesigning every system in the world and then we're going to do positioning with some and communication with the other. The perspective is that we've got a system, let's say GPS. It's already got spectrum. It's already broadcasting there. So we can't recover that spectrum and use it for our purposes. So we just can't touch it. It's off limits, but it's there. That signal is there. And so what we want to do is leverage that signal to do something more efficient in the communication link. And so I agree that there is no free lunch, but then again, I mean, we're just using what's already there. So, but if you were to redesign everything with information theory, if you wanted to do both communication and positioning, for example, you would do something different. And then there would be a trade-off, right? So you might say, well, gee, GPS doesn't need 10 megahertz. Maybe it needs 5 megahertz. And there would be a lot of other intriguing questions. And I think also that this is why I did mention that the theory does still really need to be developed here, too. I mean, it's what is the right model? Because this isn't quite geniated, but what is the model for that side information? And how do you capture the cost is not clear to me. So any other questions?
Okay.
Yes.
So we're going to talk DSRC, as you mentioned, has been around for 20 years. And most of us haven't seen any DSRC hardware. Be that as it may, you have also this issue about unlicensed spectrum in 5.9, which is licensed. And people want to put, say, some other unlicensed technology. Mm-hmm. So, that also, the point is that despite the fact that you have licensed bands, there's a great push for opening up both in millimeter waves and these sub-6 gigahertz, a lot of unlicensed bands. So that's going to create other problems of coexistence that I don't know if you...
Yeah, so the question is about, I guess, the reliability of DSRC. Is DSRC really going to happen? And what happens if that spectrum becomes shared with other services? So the way it happens right now, so there's dedicated spectrum, and it is not licensed in the sense you have to pay to use it, but it is allocated for ITS, as Intelligent Transportation Systems applications. And that spectrum sits there right at the upper end of the Wi-Fi spectrum. So Wi-Fi folks are like, hey, here's a bunch of spectrum. DSRC is not being deployed. Why don't we squeeze on over into there? And cellular folks, too, are doing the same thing. They're saying, hey, there's all this unlicensed spectrum. Why don't we put cellular there, too? And so they're trying to squeeze the Wi-Fi people out. And then both of them are trying to squeeze into any other spectrum that doesn't look like it's used. So that's a challenge. And that would make it harder for us to exploit the site information, because then when you have multiple people contending for the channel, so maybe you want to measure the channel, but it's used. You can't measure what you want. So that would have to factor in. And I think that makes actually the problem even more interesting, because you have to include that. But as far as philosophically about DSRC, I mean, so we have these collaborations with Toyota and Honda. And these are the groups that have been attending these meetings for 20 years now. And I constantly asking them this. You guys keep telling us that DSRC is great, it saves lives, it makes everything better. Well, why don't you just put it in the cars? Well, the response I get is usually something like, well, we don't want to be the first to put it in the car, because then we have to spend all this money, and then everyone else gets the benefit because our cars have it. So we're not going to do it until the government says everyone has to do it. And I don't know. I don't quite understand that. The DSRC hardware, even the stuff I've bought, is a few $100s. So I mean, I can't imagine we're talking about adding like $100 to the cost of the car, maybe. Doesn't seem like a lot, but I guess if they can't sell it, if you're not willing to buy this car over that one because it has DSRC, I guess it's not a selling point for them. So that's a strange thing. And then with the other wireless companies coming in trying to grab that spectrum, now the DSRC folks are like, hey, wait, we do want to use it. And they're trying to start deploying it to some extent just to show that they're using the spectrum. So that's a strange political situation. And now we're actually at the point where the government, it looks like, is not mandating DSRC. They're saying that cars have to have connected vehicle technology, but it doesn't have to be DSRC. And it could be cellular. So that could, in fact, erode even worse the DSRC. DSRC, I mean, I don't think it's a great technology, but it's there. It's been tested oodles of times. It's cheap. Doesn't require a fee. So I suspect it will actually be deployed in mass soon, if not for just the trying to keep that spectrum from going away. They would probably do that. I mean, I don't know. I don't know why they're not pushing more on that. But we have this question with the city of Austin. I mean, okay, should we deploy DSRC roadside units? Should we deploy 5G? Well, It's just totally different animal. But anyways, thank you for the question. Anything else? Yeah.
So in your experience looking at channel models, how stable do you think these channels will be in a mobile, like V2V, V2X situation, or is it going to be a channel that's susceptible to lots of outages despite having Genie-like techniques or trained beams?
Yeah, that's a good question. Let me see if I got my picture here. So the question is about the stability of the mobile channel, and even if with the site information, is it really usable? And so the basic question, I mean, the situation is that the propagation channel, which is measured and is a function of the wavelengths of the signal, I mean, as you move around through many wavelengths, I mean, it varies a lot. But the underlying structure, let's say the angles of arrival and departure, don't change too much. So if there's a reflector here, there's also a reflector there, and there's a reflector here. The angle changes a little bit. So what's really critical is to understand how the parameters are affected. And so the reflections and so on don't vary as quickly as the envelope of the channel itself. And so what that means is that the beam training will be good for a long period of time. Once you point the beam, you still have to estimate the channel within that beam. You do that frequently, but you don't have to repoint as frequently. But that said, I mean, millimeter wave is going to be more fragile than at lower frequencies because it's going to be sensitive to blockage. I mean, a bicycle can block the millimeter wave signal. They're not going to block it at the lower frequencies. And so that's why we need techniques for either like rapid beam switching, rapidly finding the other path. I mean, these are problems that have to be overcome. Now that said, keep in mind that even the duration of, let's say, a bicycle blocking the beam is, let's say it's like 2 seconds. I mean, when you're transmitting a gigabit per second, I mean, that's 2 gigabits of lost information. But then again, the number of bits you need to reset the link is not 2 billion bits. I mean, it's maybe a small fraction of that. So the blockage intervals from the radio perspective are an eternity. I mean, two seconds when your bit period is a nanosecond is just infinity. So it's not as bad as maybe it seems. I mean, having deep outages that were milliseconds long, that would probably be worse, I think. So I think it's overcomable, but it's going to require a lot of work. And then there was also the question of, okay, if I have to have 3 base stations now where I had 1 before, is it cost effective? And I think those are, I mean, it's all good questions. But personally, I think that there's enough stable information that we can get it to work, and we have enough systems engineering knowledge to be able to engineer it so that it can be reasonably robust. Yeah.
Okay. Okay, thanks, Robert.